We should know the reciprocal identities, the quotient identities, the Pythagorean identities, the cofunction identities, but we never learned the even odd identities. All of these were a good 70 pages ago, but we didn't need the even and odd identities until this section, so that's why we've waited to learn them until tonight. The even odd identities are a little strange in that if you'll notice, like some of them, you do like the sign of the negative angle and you get a negative of that angle, but on the others it's like cosine of the negative angle and you get a positive of that. So how come some of them are a negative of the trig function and some of them are a positive of the trig function? What causes that? Well, we can go through and just flat out memorize them. I understand that, but it would be nice if we understood the reasoning behind it because it might help us keep it straight a little bit. Let's say that we put a number in the place of that angle. So let's put 30 in the place of u. If we go through over here, we're going to get sine of negative 30 is equal to negative sine 30. All right, so when we plugged in 30 for u, we got negative 1/2 on the left, and when we plug in 30 for u, we get sine of 30, which is 1/2, so we would need that negative out in front to balance it out. So we can see the formula works. Same idea over here. If we come in and we put 30 in for u, we get square root of 3 over 2, and put 30 in for u, and we get square root of 3 over 2, so we can see that formula works. But why are they that way? How come some of them have the negative out in front and some of them don't? Well, it's this idea right here that when I have a negative 30, that means I go down 30, and when I have a positive 30, I go up 30. They're going to have the same 30-degree reference angle, so they're going to have the same trig value, 1/2 or square root of 3 over 2 or square root of 2 over 2, depending on what my reference angle might be. The key is that in the first and the fourth quadrant, sine has opposite signs, in that sine is positive in the first quadrant and it's negative in the fourth quadrant. If you think about all students take calculus, in the fourth quadrant, only cosine is positive. So everything else, other than cosine and its reciprocal secant, everything else is going to be negative in the fourth quadrant. So for cosine, because it's positive in the first and the fourth, then cosine and its reciprocal are both positive. So here's the easiest way to remember it. Whatever the sign is in the fourth quadrant, positive or negative, is what is going to be out in front of this right-hand side. So like for sine, cosecant, tangent, and cotangent, they're all going to have the negative over here. For cosine and secant, they're going to have the positive here. It's whatever their sign is in the fourth quadrant. The reason for that goes back to this diagram over here. If in the first and the fourth quadrant they have the same sign, I don't need to put in a negative to balance it out. But if in the first and the fourth quadrant they have different signs, then I would have to have that negative out in front on the right-hand side to balance my values out. Here's another way to think of this. They're called the even and odd functions by the actual definition of even odd that we learned earlier this year. Remember, we learned that an odd function is one that you can turn it upside down and it's the same thing upside down as it is right side up. Well, sine, cosecant, tangent, and cotangent, if you look at each of their graphs, you can turn them upside down and it's the same thing upside down as it is right side up. That's an odd function. We learned that the definition of an odd function was when you put negative x in the place of x in the function, you get the opposite of the original function you started with, right? So there's our actual definition of an odd function right there. Same idea with an even function. An even function was the one that was symmetric about the y-axis, meaning you folded it on the y-axis and it folded right on top of itself, right? And our definition of an even function was that if you put a negative x in the place of x in the function, you'll get the original function that you started with. So there's our definition of an even function right there, and sure enough, when you graph cosine and secant, they fold on the y-axis. They're symmetric about the y-axis. So I don't care which of those two ways you want to remember, or if you just want to make flashcards for yourself to remember these, just trying to give you some easy ways to keep those straight, but we need to learn those even and odd identities tonight. Additionally, if you've forgotten some of those other identities that are listed there on 376, we learned them like 70 pages ago. But if you've forgotten some of those, brush up on those as well, because you'll notice that in section 5.1, we're now using those identities, so we definitely have to know them to be able to use them. All right, we start off 5.1 with a bunch of review. To begin with, we want to remember some of the factoring that we've learned how to do with our trig functions in previous sections. So we're actually going to start down here with example number 5. All right, for example number 5, we've got secant squared minus 1. And we've mentioned before that sometimes when we look at the trig functions, what confuses us is the trig part of it. And so the method that we used on these before was, if you looked at that and you didn't immediately know what to do, try substituting out the trig part. So like I'm going to replace secant theta with x. So instead of secant theta squared, it would be x squared. So it would be x squared minus 1. If they told me to factor x squared minus 1, I'd have no trouble, right? That's a difference of squares. So I would just say x plus 1, x minus 1. And then that gives me a pattern for how I can solve the secant squared minus 1. It would just be secant plus 1, secant minus 1. So again, if it makes it easier for you to see, feel free to substitute those out with a variable to get the trig function out of your way. Here's another one. We've got 4 tangent squared plus tangent minus 3. Our goal is to get to the point that we can just look at that and factor it. But if we can't right now, there's nothing wrong with replacing tangent theta with a variable. So that would give me, instead of 4 tangent squared, I'd have 4x squared. Then plus x minus 3. All right, so we know how to factor 4x squared plus x minus 3. That would factor to be 4x minus 3 times x plus 1. So if we had put x in the place of tangent, then we can just put the tangent back in for x. So 4x minus 3 would be 4 tangent minus 3, and x plus 1 would be tangent plus 1. So again, we did some of that factoring before, but just wanted to review back over that because we're going to need to apply that today. Something else that we've done before is something similar to example number 1. In example number 1, they tell me that secant is equal to negative 3/2, and tangent is greater than 0, and they asked me to find all 6 trig functions. All right, so let's start with what we know. Definition of secant is r over x. Can r be negative? Yes, no? No. So if r is 3, then the x has to be the negative 1. It has to be negative 2. How do I find y? If I know x and r, yes, Pythagorean Theorem. So I'm going to go through and do x squared plus y squared equals r squared. The only problem is I don't know if y is positive or negative once I take the square root. What does it depend on? The quadrant that I'm in, yes. So I got to figure out what quadrant I'm in. They told me in the beginning that secant was negative 2/3, so I know secant is negative, and they also told me tangent was positive. So I'm going to look at all students take calculus and figure out where secant, or cosine, is negative and tangent is positive. Where is that? Third quadrant, yes. So I'm in the third quadrant. In the third quadrant, x and y are both negative, so I know I want to use a negative square root of 5. Remember, we've also said that you can just wait until the very end when you get all your values and determine the positives and negatives there if you'd rather. We'll talk about that when we get there as well. Okay, so now we can give all 6 trig functions. So we can go through, what's the definition of sine in terms of x, y, and r? What is sine? Y over r, yeah. So we're going to take y, negative square root of 5, and put it over r, 3, and that'll be our sine value. And then, of course, we can just flip it to get our cosecant, and we never leave a radical in the denominator, so we'd rationalize. All right, so then for our cosine value, what's cosine? Well, Cosine, we could use the definition, or we could use the fact that they told me secant was -3/2, and then we can flip that -3/2 to get -2/3. Work smarter, not harder. And then tangent, of course, we've got y over x. So if we take our y value over our x value and then flip it for our cotangent value. And again, not leaving a radical in the denominator. If you wanted to wait until the very end to figure out your signs, then at this stage, you could go through and say, okay, if I'm in the third quadrant, all students take only tangent's positive. So I could say sine and cosine have to be negative, tangent has to be positive, and the reciprocals would do the same thing. So I can just wait to the very end instead of having to carry it through the whole problem, whichever's easier. All right, examples 2 and 4 are also something that we've seen before, but we only worked with them very minimally. And we said that we would get to this in a subsequent chapter where we would just kind of park there. We're there. We're going to work on simplifying and verifying pretty much all week long this week. All right? So this is one of the harder things that we do all year long. It's kind of like word problems in that the only way that you get better at it is the more you do, the better that you get. So we're going to do a bunch of them today, and we're going to do some more tonight, and we're going to come in tomorrow and do a bunch more tomorrow, and do some more the next night, and it's just repetition. Once I see the same problem 5 different times, I have a clue what to do with it the next time that I see it, whereas the first couple times, I literally may be clueless, okay? So to try to give us a little bit of help here, I've given us kind of a list of suggestions over here that we can follow, and we want to follow them in that order. All right. Step number 1, we're going to look, when we're doing simplifying and verifying, we're going to look for a Pythagorean identity. Now, there on page 376, we have the basic identities, but when we learned these before, we saw they're like an equation. Like if you have sine squared plus cosine squared is equal to 1, you can subtract cosine squared from both sides, or you can subtract sine squared from both sides. You can write it a bunch of different ways. They're equations. So if you've got a trig function squared and a 1, it is almost always a Pythagorean. If you have 2 trig functions squared, a lot of times it's a Pythagorean. And that's a big time saver for us. All right, number 2, we're going to look for fractions. If I have 2 separate fractions that I could get a common denominator and put them together and get stuff to start dropping out, or if I already had a common denominator and I could break it into 2 separate pieces and get stuff to start reducing down, that might help me. Because we've already practiced with this factoring down here, we can go ahead and throw this guy in. In the textbook, they kind of throw it in a little later on after they cover the factoring. We went ahead and covered it in the beginning, so we can go ahead and throw that in now. We want to try and do any factoring that we can. And then number 3, if all else fails, change everything to sine and cosine. You can do every one of these problems typically by changing everything to sine and cosine, but a lot of times there are 2 or 3 different ways to do these problems, and changing everything to sine and cosine is the longest, hardest, most difficult of the ways. So that's why we want to use it as a last resort if everything else fails. Bottom line is do something. If you just sit here and stare at this, you're not going to get anywhere. But if you start going through these steps and putting in identities, a lot of times the thing will fall together and you didn't even see it coming. To be practical, on a test, if you don't write anything down, I can't give you any points, right? But if you do a couple of steps, I can give you a couple of points, and, partial credit is a miraculous thing. So let's look at example 2. When we talk about simplify and verify, they're very, very similar. In a simplify, you have to look in the back of the book to get your answer. In a verify, you don't. That's about the main difference, okay? I know what I'm trying to get to with a verify. With the simplify, if I go look it up in the back of the book first and know what I'm trying to get to, it's the same thing. So I'm going to use the same steps. So for this first one, if I start off by saying, okay, I'm going to look for Pythagorean identities, which would basically be a trig function squared. And so I look at my problem. I do have a trig function squared right there, but if I were to replace cosine squared with its trig identity, I would have to replace one piece with 2 separate pieces, right? It just, for some reason, doesn't feel like simplifying to me. If nothing else works, I can always come back to that. I'll use that kind of as plan B, but let me see if I got any other ideas first. All right, so then number 2, fractions. Well, I don't have any fractions over here. Step number 3, I can see if I can factor. All right, if I'm looking at this thing to factor it, this is another one of those like we were practicing with earlier today, then it might be a good idea to try substituting it out. So if I have sine, cosine squared minus sine, I might want to make that like a b squared minus a, where we're putting a in for each of the signs, and then we're putting b in for the cosine squared. Okay, so you don't have to do that, but if it just makes it easier for you to see to do that factoring, then please do. All right, so if I take out my common factor in this scenario, I would take out an a, and I would be left with b squared minus 1, right? So same story over here with my trig functions. I'm going to take out a sine, and I'll be left with cosine squared minus 1. I'm going to take out a sine, and I'll be left with cosine squared minus 1. All right, so now I can start over again with my steps and say, okay, I'm going to look for Pythagorean identities. And I have a trig function squared and a 1. We mentioned that's almost always a Pythagorean. We also mentioned that you can take these Pythagoreans and turn them around. Like if I have sine squared plus cosine squared is equal to 1, I can subtract the sine squared from both sides, and I'll have cosine squared is equal to 1 minus sine squared. If I subtract that 1 over, then I'm going to have cosine squared minus 1 equals negative sine squared. Those are just a couple of ways that I can rewrite that equation. So I'm going to replace cosine squared minus 1 with its Pythagorean identity, and that would be negative sine squared. So now I can do sine times negative sine squared, and I've got negative sine cubed. And that's as simplified as I can make it. If this had been a verify, in the beginning it would have just said verify that this is equal to negative sine cubed x. I would have known what I was trying to get to before I started. That's the only difference. Now, there is more than one way to do most of these problems. For instance, on this one, remember in the very beginning we said, step number 1, look for Pythagorean, and we mentioned, hey, I got a cosine squared. Maybe you looked at that and you did replace cosine squared with what it was equal to. What it's equal to is 1 minus sine squared. If you did that, then you would have sine times 1 is sine, and then sine times negative sine squared is negative sine cubed, and then minus sine. The sine and the negative sine would drop each other out and just leave you with negative sine cubed. Worked it a totally different way, got the exact same answer. So there's not one set right way that you have to do this. It's however you see it as you're going through and working it out. There'll be several different ways to get to that same final answer. All right, let's look at another one. For the next one, they give me a verify. Now remember, when it says verify, I can only work on one side of the equation. I can choose either side I want, but I can only work on one side until I get it to equal the other side. Okay? So this is the more complicated side. I'm going to choose to start on this side and try and make it equal cosecant. All right? So step number 1, I look for Pythagoreans, which is a trig function squared. I don't have any of those. Step number 2, I'm going to try and combine fractions. So I do have fractions. So I'm going to get a common denominator. Common denominator for 1 plus cosine and sine would just be 1 plus cosine and sine. So to get from here to here, we multiplied the denominator by sine. So I got to do the same thing to the numerator. So all we've done is multiplied that fraction by sine over sine. That's the same thing as multiplying by 1. All right? Over here, to get from the original denominator to our new one, we multiplied by 1 plus cosine. So I got to do the same thing in the numerator. Multiply top and bottom by the same thing so that I don't change that fraction. All right, if we do a little bit of simplifying, we can say sine times sine is sine squared. And then over here, cosine times 1 is cosine, and cosine times cosine is cosine squared. The purpose of creating a common denominator is to combine the numerators over the common denominator, right? So I'm going to go through and combine those numerators. So that would be sine squared plus cosine squared plus cosine. over my common denominator. And now I'm back to the top of the list again. So I'm going to look for Pythagorean identities of trig function squared. Remember we said if you have two trig functions squared or a trig function squared with a 1, that's almost always a Pythagorean. So sure enough, this one, sine squared plus cosine squared, that's this Pythagorean identity right here, right? So we could replace sine squared plus cosine squared with 1. So now in my numerator, I've got 1 plus cosine. And in my denominator, I've got sine times 1 plus cosine. So I could cancel the 1 plus cosine in my numerator and denominator. The only thing I have left then in my denominator is sine. And 1 over sine is cosecant. Now, you don't have to come over here and write cosecant, cosecant, cosecant all the way down. The only reason I did that was just to reinforce to you that we never worked on the right-hand side of that inequality. We only worked on the left-hand side until we got it to equal the right-hand side, because that's the rule for these. Remember, verify, you can only work on one side until you get it to equal the other side. So we only worked on the left-hand side until we got it to equal the right-hand side.
How did you get 1 plus cosecant?
All right, let's look at the next one. Example 6, they give me cosecant squared minus cotangent minus 3. And in a setting like this, they might ask me to factor, they might ask me to simplify, they might be asking me to verify it was equal to something else. Whatever the scenario, I have a problem. Because if I sub this out like we've been doing, where I say, okay, I'm going to replace the trig function with the variable, that would be x squared minus y minus 3. I can't solve for x and y at the same time in a quadratic. So I would either need some way of replacing x with y or replacing y with x. And the same thing is true in this problem. I need a way of either replacing cosecant squared with cotangent or replacing cotangent with cosecant. I don't have a way of replacing cotangent, but I do have an identity, one of those Pythagoreans again on 376. Cosecant squared is 1 plus cotangent squared. So if I replace cosecant squared with 1 plus cotangent squared, now everything is in terms of the same unknown. It'd be like having 1 plus y squared minus y minus 3. I can work with that. All right, so let's put our 1 and our negative 3 together. That would give us negative 2. And now we're back to having a quadratic to factor. You are always welcome to sub this out, but we would like to get to the point that we can factor these quadratics without needing to do that. This one's a good one for us to try that on. So let's try not doing like y squared minus y minus 2. Let's try working with it as it is. What are the only things that you could multiply to get cotangent squared? Cotangent and cotangent, right. And then what multiplies to be negative 2 and adds to be negative 1? Negative 2 and positive 1, and that's it. I factored it without subbing it out. So whatever you need to do, if you need to substitute it out, feel free. But try every once in a while factoring it without having to substitute. And then again, this is that one component that we use, sometimes in simplifying and verifying. Sometimes they just give us practice with factoring. All right, let's look at one more. Example 7, we've got sine plus cotangent times cosine. All right, so step number 1, if we go through our list, step number 1, we look for trig function squared. Nothing squared here. Step number 2, we look for fractions. No fractions. Step number 3, we look to see if there's something we can factor. Well, if I were going to factor this, if I subbed it out, it would be like x plus y times z, right? I can't do any kind of factoring with that. So the next thing on our list says when all else fails. Yeah, everything else has failed. So when all else fails, switch everything to terms of sine and cosine. All right, this is already in terms of sine. This is already in terms of cosine. So we just need to replace cotangent with its definition. All right, cotangent by definition is cosine over sine. And again, that's something that we already learned. That's one of those quotient identities, but it's there on page 376 as well. All right, so now everything's in terms of sine and cosine. Let's go back to the top of our list. Step number 1, don't have anything squared. Step number 2, I do have some fractions that I can work with. So let's simplify a little bit. Cosine over sine times cosine over 1 would give us cosine squared over sine. And then let's get a common denominator for 1 and sine. That would just be sine. So for this guy, to get from 1 to sine, I multiplied the denominator by sine. I got to do the same thing to the numerator. Multiply the numerator by sine. So sine times sine is sine squared. This guy we didn't have to change. Again, the purpose of getting a common denominator is so that you can combine your numerator. So let's combine those two numerators, and we'll have sine squared plus cosine squared over sine. Flashing lights should be going off. Sine squared plus cosine squared is what? 1, right. Step number 1, look for trig identities. We said if you have 2 trig squared, it's almost always one of those Pythagoreans, and absolutely, sine squared plus cosine squared is 1. And then what's 1 over sine? Cosecant. So if this had been a verify, it would have just said verify that this is equal to cosecant.